Hello, I'm Christian Chapman-Bird from the University of Glasgow, and I'm here to talk about our new approach for the acceleration of extreme mass ratio and spiral population inference with machine learning techniques. So extreme mass ratio and spirals, or EMRIs, are prospective gravitational wave sources for space-based detectors that consist of the inspiral of a compact object into a massive black hole. So what we're concerned with here in this talk is not on the parameter estimation of individual systems, but considering the population of EMRIs and what we can learn about this population from a set of detections and see what features of this population we can resolve. So the primary figure of merit for how viable population inference is the number of events that we expect to see. The most recent estimates of this event rate are fairly uncertain. However, we expect to see roughly 100 to 1,000 events per year in detector data, which is sufficiently large to motivate population inference studies for EMRIs. So population inference can take a variety of forms, but for gravitational wave population inference, we consider a Bayesian treatment. So we wish to infer some hyperparameters lambda for a population model P-pop, along with an event rate, which we assume to be Poissonian. Here we denote this n. So generally speaking, this is a fairly standard form for this kind of posterior. However, there is an interesting term entering the denominator here, which is the selection function. So this selection function essentially reweights this population likelihood according to the detectability of given populations. So this accounts for the selection biases that are present based on the detectability of event parameters as a function of parameter space. So we can compute this by computing an integral over parameter space of the population probability weighted by the detection probability. So we want to speed this up really because this could be quite slow to perform over the EMRI parameter space, which has a high number of dimensions. So we can approximate this as a Monte Carlo integral over detection probabilities evaluated for sets of parameters theta prime drawn from the population model. So the form of the detection probability can be chosen based on the search pipeline that is being used, but in the absence of a particular pipeline, we can choose this to be an SNR threshold instead, which is roughly equivalent without including complex non-Gaussian effects and things in detector data. So generally speaking, this SNR threshold can be considered as a step function where if the SNR is greater than some predetermined threshold, the event is detected, otherwise it is undetected. So generally speaking, the problem here is that we may need to compute tens of thousands of detection probabilities for a given estimation of alpha in order for our estimate with the Monte Carlo integration to be sufficiently accurate. So this means that when we need to compute alpha hundreds of thousands of times in a given population inference run, and each computation of alpha requires tens of thousands of SNR evaluations, and each SNR evaluation can take on the order of a second, we can see that this very quickly becomes impractical, and we need to look for alternative approaches which speed things up. So the primary bottleneck that we identify here is that each SNR evaluation takes 1 second, and this is including any benefits we can gain from vectorization or parallelization, and so we look to instead replace this SNR function with something faster, like an interpolant. So interpolating over the EMRI parameter space is challenging because it is 14-dimensional. We can reduce this down to roughly 10 by throwing away parameters which don't affect SNR very much, like phase, and applying distance scalings analytically post-interpolation. But this is still 10-dimensional and is challenging for classic interpolation schemes, which are forced to use grid-based methods to remain fast with such a large number of data points in the interpolation space. So even with 100,000 grid points, the number of grid points in a given dimension of the grid is still very low, and therefore the interpolation is correspondingly not particularly accurate. So what we consider instead of these methods is whether we can leverage machine learning techniques to perform this interpolation. In the machine learning world, 10-dimensional space is on the low end in terms of the dimensionalities of target spaces, and neural networks are also vectorized by construction and therefore can remain fast for computing many evaluations in a vectorized form, like we seek to with our Monte Carlo integrals. So this is a natural solution to our problem. So we perform a standard machine learning setup with a multi-layer perceptron, and we are able to achieve roughly 2 orders of magnitude in improvement compared to these other interpolation techniques without a decrease in speed. So visualizing this in another way, we can see that the neural network is able to estimate SNRs to a much higher degree of precision than the next best approach, which was linear interpolation, and also is able to do so without introducing a bias, if left unchecked, these biases could creep into the selection function estimates and therefore actually introduce a miscorrection error into our selection function, which will then have a knock-on effect for our hyperparameter estimation. So in order to actually test out our interpolator, we need a simple problem. So we choose a simple form for our population probability. Here we have some power laws for the massive black hole mass and the compact object mass, and a truncated Gaussian for the massive black hole spin. And we simply just generate a simulated catalogue from this population, and then including the detection effects, and then we perform population inference to try and recover the underlying hyperparameters. So we need a baseline to compare with, so we choose to do population inference first without including any selection bias correction, so just setting alpha to be 1 universally across the hyperparameter space. We can see that there are some strong biases present in the results. So for example, lambda mu here, which is the recall as the parallel index for the compact object mass, is deviated from the truth by roughly 0.7, which is quite significant compared to the width of the posterior. This is expected because the compact object mass and SNR are strongly correlated, but there are some other biases and other parameters as well. But when we include our bias correction with the neural network, we can see that these biases are strongly corrected for and are consistent with the truth. And we also estimate the event rate quite precisely as well. So this, unfortunately, due to the nature of the Monte Carlo integral and needing to draw for each event, for each hyper-posterior sample, we need to draw 10 to the 4 sets of parameters to plug into our neural network. Sampling slowed down by roughly a factor of 100, even despite the improvements that we are able to make with the neural network. So to address this, we actually train a second neural network on these Monte Carlo estimates prior to sampling. So you specify a prior for your hyperparameters, draw from the prior, and compute with the first network sets of selection function estimates. Then train a second network on this and use this second network for your actual sampling. And this was able to achieve very, very similar results. You can see here that they are virtually identical, but we are able to restore sampling speeds to that of the uncorrected case. So we are able to correct for selection biases here with no detriment to runtime of the analysis, which allows you to use more complicated population models. So in general, we have been able to show that you are able to train a neural network to interpolate over SNR functions even for complicated waveforms and high dimensional spaces, and achieve high precision with low runtimes. We show this, demonstrate this in a test population inference problem, and we correct for the selection biases which are present, and we are able to incorporate a second stage network that learns the selection function to keep sampling efficient and fast. And as a bonus, this is completely independent of what waveform model you choose to use, and indeed what population model you choose to work with. And therefore you are able to apply this technique for any models that you choose, really. So we aim to release the tools to do this in the future in a standalone code package along with the publication of this work. Thanks very much.